In this video, we're going to look at functions of two variables. Specifically, let's start with functions of x and y, which are the most common. So suppose a company produces x units of one product and they make a profit of $3 for each one sold, and the same company produces y units of a second product and they make a profit of $5 for each one sold. Well, then your total profit is the sum of the profit that you make from selling the first product plus the sum of the product that you make plus the profit that you make from the second product. So your total profit P is a function of both x and y. So x and y are both inputs to the function P. It would equal, let's see, $3 for each of the x units sold, so 3x, plus $5 for each of the y units sold, so 5y. The domain is the input. Okay, the input, which is usually an x comma y ordered pair, at least if you have a function of two variables, that's what it's going to look like. The range is the output, or the set, I should say the set of x, y that you can input. The range is the set of output values, typically referred to as z, okay, or the function itself. What does this look like when you graph that? Well, on an xy plane for a function of one variable x, you get just a point in 2 space. You have x on this axis and y on this axis. In 3 space, it typically looks like this. The x-y axis, x is kind of drawn out of the paper a little bit. Y goes out to the right, and z goes up. Okay, so you have to view it kind of three-dimensionally here. You've got 3 dimensions in 3 space. So your x, then your y, and then up and down is your z. Okay, so although we're not going to really be plotting points much, this is just to get a basic understanding here of the 3-dimensional axes. We're going to plot these 4 points. Okay, so we're going to start by plotting, by sketching the axis. So let's go with the z-axis there, the y-axis there, and it's typical to only draw the positive half of each axis, and the z-axis coming out of the paper at us, right? I mean x-axis coming out of the paper at us right there. Okay, we're going to draw everything out to 5. If you drew the negative axes, it would just get too messy, typically. So the point 4, 3, 0, for that we go 4 out in the x direction. And now here's where you have to use your imagination a little bit. Although 1, 2, 3, 4 is right here on the y-axis, that is not where the point 4, 3, 0 is, because we're looking at this three-dimensionally. So we need to go out 4 on the x-axis and then over about the equivalent of 3 units, okay, so that it lines up like so. Okay, so there's the point P1, 4, 3, 0. P2 is the point 4, 3, 5, so we take that point and we're going to go up, straight up, the equivalent distance of 5 points, so about that far. And I'm just eyeballing it here, maybe about like that. Okay, that's the point P2. P3 is the point 0, 5, 2. So you go 0 in the x direction, 5 in the y direction, and up 2 in the z direction. That's a little bit easier to plot. Okay, and then this P4 is a little bit challenging to plot. To go 2, -2, -4. So we're going to go 2 in the x direction, -2 in the y direction is about like so, and then down, straight down 4 units roughly. This is way about down there. Okay, what do graphs of functions in 3 variables look like? Well, they're typically surfaces. Okay, this is a plane, a 3-dimensional plane. This one is parallel to the y-axis. This one's parallel to the x-axis. You can get things like this, a paraboloid, a hyperbolic paraboloid. This one's kind of cool. These are just basic shapes, right, to give you an idea of what kinds of graphs you might see in their equations here. It's kind of neat. Okay, but one example that I'd like to look at is the Cobb-Douglas production function, because this has an application in the business world. So in the 20s, Charles W. Cobb and Paul H. Douglas constructed this function, and it's useful for production studies when you're trying to figure out how many units of input, such as units of labor and units of capital, are needed to produce a certain number of units of the product. And you can use this to analyze, the effect of a change in your unit of capital and how that produces your production, and versus a change in your capital and how that affects production. It's pretty nice. Typically, X represents the number of units of labor used to produce the product in question, and Y represents the number of units of capital used to produce the product. F of XY, your output, is the number of units that you are producing. So the Cobb-Douglas production function is given by the following. F of XY equals a constant C times X to the A times Y to the A minus 1, where little a is some constant in between 0 and 1, and the exponents on the x and the y, interestingly, will always add to 1.